On the morning of February 19, 1945, a silver P-51 Mustang descended through broken clouds over the Kanto Plain, trailing a thin ribbon of white smoke from its Packard Merlin engine. Lieutenant Thomas Callahan of the 339th Fighter Squadron had already resigned himself to the inevitable when his oil pressure gauge dropped to zero somewhere over Chiba Prefecture. He would never know that his forced landing in a frozen rice paddy would set in motion a discovery that would fundamentally alter how Japanese engineers understood not just American aircraft, but the entire industrial philosophy that was slowly grinding their nation toward defeat. 8,000 meters below, in a converted textile factory on the outskirts of Nagoya, a team of metallurgists had spent the previous 14 months attempting to solve a problem that seemed to grow more insurmountable with each passing week. Dr. Kenji Yamamoto, the team's leader and a former professor at Tokyo Imperial University, had been tasked with understanding why Japanese aircraft aluminum failed at stress points where American aluminum did not. The answer, he believed, lay somewhere in the molecular structure of the alloys themselves. What he could not have anticipated was that a single crashed fighter would reveal truths far more profound than the composition of metal. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What Dr. Yamamoto and his team would discover over the following 6 weeks would shatter their assumptions about American manufacturing, reveal the true nature of industrial superiority, and ultimately convince them that the conflict they were fighting had been decided not on any battlefield, but in laboratories and factories they had never imagined existed. This is the story of how a single aircraft joint transformed the understanding of engineers who had believed their nation's defeat was a matter of resources, only to learn it was something far more fundamental. The telephone call came to Dr. Yamamoto's office at precisely 9:14 in the morning on February 20th. Colonel Takeshi Fujimoto, the Army liaison officer assigned to the Metallurgical Research Division, spoke in clipped, urgent tones. An American fighter had come down largely intact near the town of Sakura. The pilot had survived and been taken into custody, but more importantly, the aircraft itself was in remarkable condition considering the circumstances of its landing. The Army was transporting it to the Mitsubishi facility in Nagoya, and Dr. Yamamoto's team would have first access to examine its construction. Yamamoto replaced the telephone receiver and sat motionless for several moments. In 14 months of research, his team had worked exclusively with fragments recovered from aerial engagements over the home islands. Twisted, burned, often barely recognizable pieces of aluminum that had been subjected to the violence of combat and the subsequent trauma of impact. An intact aircraft represented something entirely different. It was the difference between examining a single torn page from a novel and being handed the complete manuscript. He gathered his 3 senior researchers in the cramped conference room adjacent to the main laboratory. Dr. Hiroshi Tanaka, an expert in crystalline structures, arrived first, followed by Dr. Akiko Sato, whose specialty was stress analysis, and finally Dr. Masahiro Endo, who had spent a decade studying industrial heat treatment processes before the conflict had redirected his career toward military applications. "I have just received word," Yamamoto began, "that we will have access to a largely complete American fighter within the next 48 hours. A P-51 Mustang. I want each of you to prepare a list of specific examinations you wish to conduct. We may not have extended access, so we must prioritize ruthlessly." Dr. Tanaka leaned forward, his eyes bright with professional interest. "The wingroot joints," he said immediately. "Everything we have examined suggests their aluminum alloys behave differently under torsional stress. If we can examine an intact joint assembly, we may finally understand why." Dr. Sato nodded in agreement. "The Americans are building these aircraft at a rate we cannot match. If there is something in their metallurgy that allows for faster production without sacrificing structural integrity, we must identify it." Dr. Endo, the oldest of the group at 53, spoke more cautiously. "We should prepare ourselves for the possibility that what we find will not be encouraging. Every fragment we have examined suggests a level of quality control that exceeds our current capabilities." Yamamoto acknowledged the concern with a slight inclination of his head. Whatever we discover, our duty is to report it accurately. The path to improvement begins with honest assessment. The aircraft arrived at the Nagoya facility on the morning of February 22nd, transported on a specially modified rail car under heavy guard. Yamamoto and his team were waiting on the loading platform when the tarpaulins were removed, and even these experienced engineers found themselves momentarily silenced by what they saw. The Mustang rested on its belly, its landing gear having collapsed during the forced landing, but otherwise it appeared almost ready to fly. The distinctive bubble canopy was intact, the propeller blades bent but attached, and the long, graceful fuselage showed only superficial damage from its slide across the frozen paddy. Most importantly, the wings remained attached to the fuselage, their structural integrity apparently uncompromised. It took 6 hours to move the aircraft into the secured examination hangar using a system of cables and rollers. By evening, the Mustang sat beneath banks of electric lights, surrounded by tool carts and examination tables. Yamamoto had arranged for his team to have exclusive access for 72 hours before Army technical intelligence officers would arrive to conduct their own assessment. "We begin with the wingroot joints," Yamamoto announced. "Dr. Tanaka, you will lead the examination. Dr. Sato will document stress patterns. Dr. Endo will prepare samples for heat treatment analysis. I will coordinate and maintain the examination log. The wingroot joint of any aircraft is among its most critical structural elements. It must bear the entire aerodynamic load of the wing, while simultaneously allowing for the flexion that occurs during flight. In a high-performance fighter like the Mustang, these joints were subjected to enormous and constantly varying stresses as the aircraft maneuvered. Japanese engineers had long struggled with failures at these points, and the examination of this intact example represented an unprecedented opportunity. Dr. Tanaka approached the port wing root with a powerful magnifying lamp and began his visual examination. For nearly 20 minutes he said nothing, moving the lamp slowly across the joint assembly, occasionally making small sounds of interest or surprise. Finally, he stepped back and turned to his colleagues. "The first thing I notice," he said carefully, "is that the joint appears to be assembled from considerably more individual components than our equivalent designs. I count at least 14 separate pieces of hardware where we would typically use 5 or 6. More components means more points of potential failure," Dr. Sato observed. "Why would they complicate the design in this way?" "That," Tanaka replied, "is precisely what we must determine." Over the following hours, the team carefully disassembled the wingroot joint, documenting each step with photographs and detailed drawings. What emerged was a picture of engineering philosophy that differed fundamentally from Japanese practice. Where Japanese designers sought to minimize the number of components in an assembly, American designers had embraced complexity. Each individual piece was simpler than its Japanese equivalent, but collectively they formed a system of remarkable sophistication. By midnight, the team had removed and catalogued 43 individual components from a single wing root joint. Laid out on examination tables, they represented a puzzle that the engineers were only beginning to understand. "Look at these bolts," Dr. Endo said, holding one up to the light. "The threading is perfectly uniform, every single one. I have examined 7 bolts from this joint and I cannot distinguish between them without checking the markings." Dr. Sato had made a similar observation about the aluminum structural members. "The tolerances are extraordinary," she said. "I am measuring variations of less than 0.05 of a millimeter between supposedly identical parts." Yamamoto felt a cold sensation forming in his stomach. He was beginning to understand what they were seeing, and the implications were troubling. "Let us continue the examination," he said. "We must be thorough before drawing conclusions." The following morning, Dr. Tanaka began his crystalline structure analysis of the aluminum alloy samples. Using the facility's electron microscope, he examined cross-sections of the structural members at magnifications that revealed the molecular arrangement of the metal itself. What he found left him sitting motionless before the microscope for nearly 30 minutes. When he finally spoke, his voice was subdued. "The grain structure is uniform throughout the entire sample," he said. "Not just similar, uniform. The heat treatment process that produced this metal was controlled to a degree I would not have thought possible in industrial production." Dr. Endo joined him at the microscope. examining the same samples. He emerged equally shaken. "This is not simply good metallurgy," he said. "This represents a level of process control that requires instrumentation and standardization far beyond anything in our current production facilities." Yamamoto requested clarification. "Explain what you mean by process control." Hendo gathered his thoughts before responding. "When we heat-treat aluminum alloys, we attempt to control temperature and duration to achieve desired properties, but our furnaces vary, our thermometers vary, our timing varies. The result is that each batch of metal is slightly different from the last. We compensate through over-engineering. We make things stronger than they need to be to account for inconsistency." He gestured toward the microscope. "This metal shows no such variation. Every sample from this aircraft displays identical grain structure. That means their furnaces maintain exact temperatures. Their timing is precise to the second, and their raw materials are consistent from batch to batch. They are not over-engineering to compensate for variability. They have eliminated the variability itself." The implications of this observation rippled through the team over the following hours. If American manufacturers had truly achieved this level of consistency, it explained why they could use more complex assemblies without sacrificing reliability. Each individual component could be trusted to perform exactly as designed because it was manufactured to exact specifications every single time. Dr. Sato conducted stress analysis tests on removed components and found further evidence of this precision. The American parts showed stress distribution patterns that matched theoretical ideals almost perfectly. Japanese equivalent parts, by contrast, always showed slight irregularities that reflected the variability in their manufacture. By the evening of their second day with the aircraft, Yamamoto convened his team for a preliminary assessment. The mood in the conference room was somber. Each researcher had arrived at similar conclusions through different avenues of investigation, and the picture that emerged was not encouraging. "Let me summarize what we have learned," Yamamoto began. "The American wingroot joint uses more components than our designs, but each component is manufactured to tolerances that ensure perfect interchangeability. This means that any part can be replaced with any other part of the same type without fitting or adjustment. It also means that assembly requires less skilled labor because workers are not required to compensate for variations in the parts they are installing." He continued, "The metallurgy of their aluminum alloys shows process control that eliminates batch-to-batch variation. This allows them to engineer to exact specifications rather than over-engineering to account for inconsistency. The result is aircraft that are simultaneously lighter, stronger, and more reliable than our own." Dr. Tanaka added a further observation. "I have examined the markings on many of these components. They come from at least 7 different manufacturing facilities across the United States, yet they fit together perfectly. This means their standardization extends not just within individual factories, but across their entire industrial base." The room fell silent as the implications sank in. This was not simply a matter of the Americans having more resources or more workers. It represented a fundamentally different approach to manufacturing, one that had transformed industrial production into something approaching scientific precision. Dr. Sato spoke the thought that was in everyone's mind. "If they can manufacture aircraft components to this standard," she said quietly, "they can manufacture everything to this standard. Engines, vehicles, weapons, ships, their entire military output benefits from this approach. And they can train workers faster," Dr. Endo added. "If parts are truly interchangeable, assembly becomes a matter of following procedures rather than exercising craft skills. A worker can become productive in weeks rather than months." Yamamoto nodded slowly. "We came here hoping to discover why American aluminum performs better than ours. What we have discovered is that the aluminum itself is only part of a much larger system. The true advantage lies in their ability to translate designs into reality with absolute fidelity, thousands of times over, across dozens of facilities, with workers of varying skill levels." The third day of examination confirmed and extended these findings. The team disassembled additional joints and assemblies throughout the aircraft, finding the same patterns of precision manufacturing everywhere they looked. Control cables showed identical tensions. Hydraulic fittings showed identical thread patterns. Even the rivets displayed a uniformity that Japanese production could not match. Dr. Tanaka made one final discovery that seemed to crystallize everything they had learned. While examining the cockpit area, he found a small aluminum plate bearing manufacturing information. The plate indicated that this particular aircraft was the 4673rd P-51 Mustang, produced at the Inglewood, California facility, a production number that staggered the imagination. He brought the plate to Yamamoto without comment. The two men looked at it for a long moment. 4,673, Yamamoto said quietly, from a single factory. And that is only one of several facilities producing this aircraft. He thought of Japan's total fighter production across all manufacturers and all types. The numbers were not comparable. But more importantly, he now understood that the numbers alone did not capture the true disparity. American factories were not simply producing more aircraft. They were producing better aircraft, more efficiently, with less skilled labor and fewer resources per unit. The gulf between the two industrial systems was not merely quantitative, it was qualitative. On the morning of the fourth day, Colonel Fujimoto arrived to inform Yamamoto that Army Technical Intelligence would be taking custody of the aircraft that afternoon. The metallurgical team had a few hours remaining to complete their examination. Yamamoto used the time to conduct one final inspection, walking slowly around the Mustang with a notebook, recording his thoughts. The aircraft sat silently under the lights, its silver skin gleaming where it had been cleaned for examination. It was, Yamamoto reflected, a beautiful machine. The Americans had created something that was simultaneously a weapon of war and an achievement of engineering art. Every line served a purpose. Every component fit precisely where it belonged. It represented the full mobilization of industrial capability in service of a single objective. He thought of Lieutenant Thomas Callahan, the pilot who had brought this machine down in a frozen rice paddy rather than abandon it over open water. The American was currently in a detention facility somewhere in the city, and Yamamoto found himself wondering what the man knew about the systems that had produced his aircraft. Probably very little, he decided. The pilot would know how to fly the machine, how to maintain it, how to fight with it. But the vast industrial apparatus that had created it would be largely invisible to him, as water is invisible to a fish. That afternoon, Yamamoto convened his team one final time before they returned to their primary research facility. They sat around the conference table, each lost in thought, contemplating what they had learned and what it meant. "I have been asked to prepare a report for the Army Technical Committee," Yamamoto said. "I would like each of you to contribute a section addressing your specific findings. But before we begin that work, I want to discuss what we will recommend." Dr. Endo spoke first. "We must be honest about what we have seen. Any attempt to minimize or obscure these findings would be a disservice to those who must make decisions based on our report." Yamamoto nodded. "I agree completely. But honesty includes identifying potential responses to what we have learned. Simply cataloging American advantages accomplishes nothing if we cannot suggest paths forward." The discussion that followed was both technical and philosophical. The team considered various approaches to closing the manufacturing gap they had identified. Could Japanese industry adopt American methods of standardization and quality control? Could the training of workers be modified to emphasize procedure over craft? Could inspection and measurement techniques be improved to achieve greater consistency? Each suggestion ran into obstacles. Standardization required coordination across multiple manufacturers who were accustomed to working independently. Quality control required instruments and techniques that Japan did not possess and could not easily develop under present conditions. Training reforms required time that was not available. Dr. Sato raised another consideration. "Even if we could implement these changes," she said, "we would be attempting to match where they were when this aircraft was built. Their methods continue to improve. By the time we achieved their current capabilities, they would have advanced further still." It was a discouraging but accurate observation. The American industrial system was not static. It was learning and improving continuously, incorporating feedback from the field, developing new techniques and technologies. Catching up to a moving target was far more difficult than matching a fixed standard. Yamamoto listened to his team's discussion without interrupting, allowing them to work through the implications themselves. When the conversation finally wound down, he offered his own perspective. "What we have witnessed," he said, "is not simply superior manufacturing. It is a different relationship between design and production. In our system, designers create plans and craftsmen interpret them, using their skills to compensate for limitations in materials and processes. In the American system, the process itself has been engineered to execute designs faithfully. The workers serve the system rather than the system depending on the workers." He paused, choosing his next words carefully. "This approach requires enormous investment in the means of production. Precision machines, standardized measurements, quality control procedures, training programs. The Americans have made these investments over many years, and they are now realizing the returns. We cannot replicate in months what they have built over decades." "Then what do we recommend?" Dr. Tanaka asked. Yamamoto had considered this question carefully. "We recommend 3 things. First, that this examination be shared with senior leaders so they understand the true nature of the industrial disparity we face. Second, that immediate efforts focus on improving quality control within our existing capabilities, even if we cannot match American standards. Third, that planning for the future include fundamental reconsideration of our manufacturing philosophy, recognizing that true competitiveness requires not just more production, but better production systems." He looked around the table at his colleagues. "And we must be prepared for the possibility that our recommendations will not be welcomed. People do not like to hear that problems are larger than they believed or that solutions are more difficult than they hoped." The report was completed within a week and submitted to Colonel Fujimoto for transmission to the Army Technical Committee. It was thorough, detailed, and unsparing in its assessment. The team documented their findings with photographs, measurements, and analysis. They included comparisons with Japanese equivalent components that made the disparities clear and quantifiable. The response came more quickly than Yamamoto had anticipated, and from a higher level than he had expected. 10 days after submitting the report, he received a summons to appear before a panel of senior officers and industrial leaders in Tokyo. The meeting would take place at the Army Ministry, and his presence was required within 48 hours. Yamamoto traveled to Tokyo by overnight train, using the journey to review his notes and prepare for questions. He arrived at the Army Ministry building on a grey March morning and was escorted to a conference room where 9 men sat around a long table. He recognized some of their faces from photographs in newspapers. These were men who made decisions that affected millions of lives. The questioning began immediately and continued for nearly 3 hours. Yamamoto was asked to explain his findings, to justify his conclusions, to defend his recommendations. Some of the questions were technical, probing the details of his metallurgical analysis. Others were strategic, asking about implications for production planning and resource allocation. A few were almost accusatory, suggesting that his report was defeatist, or that he had failed to identify ways to counter American advantages. Yamamoto answered each question as completely and honestly as he could. He did not minimize difficulties or exaggerate possibilities. When asked directly whether Japan could match American manufacturing quality, he replied that it could not be done with existing resources and methods in the time available, but that improvements were possible that would narrow the gap. When asked about the morale implications of sharing his findings more broadly, he replied that soldiers and workers deserved to understand the challenges they faced, and that false optimism was more dangerous than difficult truths. The meeting ended without clear resolution. Yamamoto was thanked for his work and dismissed. He returned to Nagoya uncertain whether his report would lead to action or be filed away with countless other technical documents that had failed to penetrate the layers of bureaucracy and wishful thinking that insulated decision-makers from uncomfortable realities. In the weeks that followed, Yamamoto continued his research, but his focus had shifted. He was less interested now in the specific properties of aluminum alloys than in the systems that produced them. He began corresponding with colleagues in other industries, asking about their experiences with quality control and standardization. The responses confirmed that the patterns he had observed in aircraft manufacturing extended throughout Japanese industry. Variability was accepted as inevitable. Craftsmanship was valued over consistency. Processes were not measured or controlled with scientific precision. Dr. Tanaka, meanwhile, had become almost obsessed with the concept of interchangeability that the Mustang examination had revealed. He spent hours calculating the implications for production efficiency. If any part truly fit any assembly, he explained to Yamamoto, then factories do not need to produce matched sets. They can build inventories of individual components that can be combined in any configuration. This simplifies scheduling, reduces waste, and allows faster response to changing requirements. Dr. Sato pursued the human implications. She visited several aircraft factories and observed the workers on production lines. What she saw confirmed the team's hypothesis. Japanese workers spent significant time fitting and adjusting components because the parts they received varied from piece to piece. This required skilled workers and consumed hours that could otherwise be spent on additional production. American workers, she inferred from the evidence of the Mustang, must be able to assemble components much more quickly because the parts simply fit. Dr. Endo took a longer view. He began researching the history of American manufacturing, reading whatever translated materials he could find about mass production techniques. What he learned was that the approach they had observed in the Mustang had roots going back nearly a century to the production of firearms and sewing machines. The Americans had developed interchangeable parts manufacturing long before anyone else, and had refined it continuously ever since. Their current capabilities represented generations of accumulated knowledge and investment. This is not something they invented for the present conflict, Endo told Yamamoto. It is how they have built things for longer than any of us have been alive. We are facing not just their current strength, but their entire industrial tradition. As spring arrived, bringing warmer weather and the resumption of large-scale air operations over the home islands, Yamamoto reflected on what the Mustang examination had taught him. The specific findings about aluminum alloys and joint designs were important, but they were not the true lesson. The true lesson was about systems and philosophies, about fundamentally different approaches to the relationship between human skill and industrial processes. Japanese manufacturing relied on the craftsman as the source of quality. A skilled worker could take variable materials and imperfect tools and produce excellent results through the application of knowledge and experience. This approach had deep cultural roots and had served Japan well in many contexts, but it did not scale. The craftsman could teach apprentices, but there were only so many craftsmen and only so many hours in the day. Quality depended on individuals, and individuals were limited. American manufacturing had externalized quality from the individual worker to the system itself. Precision machines, standardized measurements, controlled processes, and rigorous inspection meant that quality was built into the production method rather than added by the producer. This approach scaled almost indefinitely. Once a system was established and validated, it could be replicated and operated by workers with modest training. Quality depended on the system, and the system could be expanded as needed. Yamamoto wrote a second report, a more reflective document that attempted to explain these deeper implications. He knew it would be less well received than the first, which had at least dealt with concrete technical matters. This second report ventured into territory that touched on culture and tradition, questioning approaches that had defined Japanese industry for generations. He was right about the reception. The second report was acknowledged, but generated no invitation to Tokyo, no panel of senior leaders seeking clarification. It disappeared into the bureaucracy, perhaps read by a few technical officers, perhaps filed unread. The war continued, the air raids intensified, and the questions Yamamoto raised about manufacturing philosophy seemed increasingly irrelevant to a nation focused on immediate survival. But Yamamoto continued thinking about what he had learned, even as the situation deteriorated around him. In June, his research facility was relocated twice to escape bombing. In July, most of his team was reassigned to direct production support. By August, he was working largely alone, conducting what research he could with damaged equipment in a makeshift laboratory. The end, when it came, brought a strange mixture of devastation and relief. Yamamoto learned of the surrender while sheltering in a basement during what would prove to be the final air raid alert. He emerged into a world that had been transformed, a nation that would need to rebuild everything from the ground up. In the months that followed, as the occupation began and the long process of reconstruction started, Yamamoto found that his wartime research had given him an unexpected perspective. He understood what needed to change if Japan was to build a new industrial foundation. The lessons of the Mustang wing root joint, the implications of standardization and quality control, the power of systems over individual craftsmanship, these insights now had a context in which they could be applied. He was not alone. Many engineers and industrialists had reached similar conclusions through their own experiences during the conflict. They had seen American equipment, studied American methods, and understood that Japan's future competitiveness required fundamental transformation of its manufacturing approach. The defeat had been a harsh teacher, but it had taught lessons that would shape the nation's economic recovery for decades to come. Dr. Tanaka became a consultant to several manufacturing companies, helping them implement standardization programs and quality control systems. Dr. Sato turned her attention to industrial training, developing methods for teaching process discipline to workers accustomed to relying on individual judgment. Dr. Endo wrote extensively about the history and principles of interchangeable parts manufacturing, translating American technical literature and making it accessible to Japanese industry. Yamamoto himself was invited to join a government advisory committee on industrial reconstruction. In this role, he helped shape policies that encouraged standardization across industries, promoted investment in precision measurement and quality control, and established technical training programs. The transformation he had recommended in his wartime reports began to take shape, though it would require years to fully realize. He sometimes thought about Lieutenant Thomas Callahan, the pilot whose forced landing had started everything. Yamamoto never learned what happened to the American after the war ended. Perhaps he returned home to a country that had no idea how its industrial strength had appeared to those on the receiving end. Perhaps he flew commercially, or worked in aviation, or never thought about airplanes again. His brief presence in Japan had set in motion a chain of events that would have consequences he could never have imagined. And Yamamoto thought about the Mustang itself, that silver machine that had revealed so much. It had been a weapon of war designed to establish air superiority and strike at enemy production. But it had also been an unintentional teacher, a physical embodiment of industrial principles that Yamamoto and his team had studied and learned from. In examining that aircraft, they had discovered not just how to build better airplanes, but how to build better systems for building anything at all. The wing root joint that had started their investigation had been a masterpiece of engineering, not because any single component was remarkable, but because every component was exactly what it was supposed to be. 43 pieces of metal and hardware that fit together perfectly because each had been manufactured to precise specifications and held to exact tolerances. It was a small thing, a connection between a wing and a fuselage, but it represented an entire philosophy of production. Decades later, when Japanese manufacturing had become renowned worldwide for its quality and precision, when the student had in many ways surpassed the teacher, Yamamoto occasionally wondered if anyone remembered how it had started. The journey from that basement laboratory to global industrial leadership had been long and had involved countless people and decisions, but for him, it had begun with a single crashed aircraft in a frozen rice paddy and the 43 components of a wing root joint that had changed how he understood the world. The story of the Mustang examination was not really about metallurgy or even about manufacturing. It was about the moment when assumption gives way to understanding, when what you thought you knew is replaced by what you actually see. Yamamoto and his team had begun their work believing they were investigating a technical problem with aluminum alloys. They had ended it understanding that they were witnessing a fundamentally different approach to transforming ideas into reality. That understanding had been painful at the time, an acknowledgement of disadvantage that seemed insurmountable. But it had also been the necessary first step toward change. You cannot improve what you do not honestly assess. You cannot close a gap you refuse to see. The Mustang had forced Yamamoto to see clearly, and that clarity, however unwelcome, had proved to be the most valuable thing the aircraft could have provided. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.